Hello, everyone. This week, we are talking about randomness and random values, which sounds easy, and it's a fairly easy concept, but we can do some interesting things with it. And from here, we will be designing some experiments for us to use and do science with. But we also will discuss some of the problems that come with that. And the problem is computers are deterministic. And when they're not deterministic, meaning that the same input will give us the same output every time, we get pretty cranky pretty quickly. So, how can we have randomness in a deterministic system? Yeah, it's a problem. So, encryption does need true random numbers. Computers do not have true random numbers. And I will fully admit that even the pseudo random number algorithms are outside of my range of understanding. They're beautiful, complicated. There is bad things that happen when poorly chosen random numbers happen. If you can have predictable next numbers in your random set, well, these are links. One of them, you can basically predict how to get onto somebody's Wi-Fi, and this is called nonce reuse. And nonce is you encrypt a random value and then send that as a challenge, and then you get a response. And if you resend the same challenge, well, then attackers can get enough material to be able to break your password and your encryption. Cool. There is a general problem, just random number generator attacks. There is a whole swath of problems here, including PlayStation 3. I don't think I've actually known about that one. Cool. You can see more nonce stuff, which is always exciting. And this is bad. This will make your what should be private browsing experience not private. And, well, if you want to get into this, there's a lot here. But in general, we can't have true random numbers. They don't exist in computer systems. We're done. But can we do good enough? Well, we can. It is not pure randomness. It is pseudo-random numbers. They are pseudo-random numbers. So we have a pseudo-random number generator. And pseudo does mean fake. These are pretty much random numbers. Don't use these for encryption. Don't. If you're doing your own encryption and writing that yourself, you're either doing it wrong or you're in a PhD program or you're working for the National Defense. Outside of that, just use the libraries, please. We have this problem of having pseudo-random numbers, meaning that they're fake, which means that they're predictable. And that doesn't make sense. Predictable randomness isn't randomness. Well, that's exactly the point. We have something called the Mersenne twister. I pronounced that wrong because I'm way too English. I apologize. And this will generate passwords. 2 to the 19,937 minus 1 random numbers. And you could use them as passwords. I was on a password run. Before repeating the sequence. It will repeat individual numbers within that set. Look into the pigeonhole principle. If you are, depending on what you're asking to give you, there's going to be duplicates and even repeated sequences. But from wherever we are, we can't predict the next number. And that's what we need. I get to draw things. And my hotkeys aren't working. So there. So this looks something like this. We have a start point. We'll see that this is actually the seed. And we will start choosing random numbers. And we will keep on going around this until we ask for 2 to the 19,937th number, at which point then it will start repeating. If you're writing a program that requires 2 to the 19,937 random numbers, you're going to have to choose a better random number generator. For all the normal people that are sitting at home, I could say in class, in your digital class, this is fine. This is totally okay. But there is an interesting outcome of this. When we start again, what happens? Well, we start again in the seed, we will get the same random numbers. Oh, well, that's not what we want usually. Usually we just want to have random numbers. And that's fine. The random library can do that for you. But if you're doing science, you actually want the same random numbers every time. And what do I mean by that? We actually want repeatable science. So when we're doing experiments with random events, what we need is the same random events for every simulation. And that sounds really weird. So how can I show you that? So imagine a simulation where you have multiple days, and I'll solve this problem for you in code eventually. And there is a number of customers that want to buy something. And we have a product, and we make a certain number every day. Okay. Well, what we want here is a random number of people every day. And over here, we want to be able to do, and this is very loose science, do trials for different amounts. So what we would have on day 1 is a randomly chosen number of people to buy things, and we're going to make, say that these are pies, we're going to make 4 pies. And day 2, we're going to have some other random number of people who want to buy pies, and we're going to make 5 pies. And then 3, we have some random number, and we're going to make 6 pies. Well, now we can have random numbers slotted in. We're going to say that there's 10, 2, and 6. We can run multiple trials with different numbers here, and we can maximize our profits and minimize our losses by doing some simulations. And then after that, we can start changing this. What if we started getting more business? What kind of predictions, what kind of outcome should we create? So that is actually some very loose and not super powerful, but is science. We want the same random events so we can actually do apples to apples. Always get the same start point, always have those same number of random customers, but we can change our tunable, like the thing that we actually want to change. And to do this, we're going to do something called seeding the random generator. So on that big old circle I drew, I said start point. This is the seed. This is our start point. We're going to start at spot 1, 2, 3, 4. Choose your favorite number. And that will be where you start. And then from there, you can always get the same random events and then do different things with them. So this is actually interesting. So we can actually start making hypotheses and start proving or disproving hypotheses based on our changes to the parts that we can control. And then we have the random thing that will actually go through our system. Okay, so random library. Let's look at some code. Random.random. Pretty random. This is very general. It'll return you a number from 0 up to and not including 1. And now you're sitting there thinking, that's dumb. It feels that way, doesn't it? But what this gives us is a continuous and flat distribution. And from there, we can change our distribution to fit our problem set. So we can say, well, if we want numbers from 1 to 10, we can just multiply this number by 10. And it'll be random numbers from 0 up to and not including 10. And then we can force those into integers. And then we've now made a program that is 0 to 9 randomly chosen integers. So we can flex our distribution to fit our problem. So it is super duper general, and we're going to play around with that a little bit. It is actually kind of nice. But of course, Python is kind. Why would I have to write my own random integer method when one exists? Though it makes me very angry. There's a programming pattern that says you have a start point A and you go up to and not include the endpoint B. Look at random range from 0 up to and not including 1. Okay, that's just like arrays. That's just like a string. That's all of these things. We started at 0, 1, up to and not including the number for length. This one's inclusive. It makes me very angry. Random by choice. Pass it a list. And it'll randomly choose an element out of your list. It's actually pretty easy to do yourself, given randint exists, but it gives it to you for free. And we'll do some demos on how to use each one of these later. This is just for awareness right now. So how do we do it? Set a seed, create an experiment, and do a bunch of trials. For example, how long would it take us? How many rolls? And we can do a simulation. We could do this mathematically. I apologize for any mathletes in the crowd. How many rolls would we have to take before we roll a Yahtzee? Okay, let's find out. We can make an experiment, and we can actually mathematically model this, and that would probably be our hypothesis. The hypothesis that our mathematical model, which is pretty simple statistics, is correct, and then we will validate that using simulation. So, there it is. My hotkeys aren't working. I apologize. Okay, import random. This will import everything we need to do random stuff. And we have loops at our disposal. And what is a Yahtzee? For those who've not played Yahtzee, you roll 5 dice, and a Yahtzee is when all 5 match. Okay. This works for us. So I'm going to make a function because I do want to write everything in functions. This is actually pretty important, where I'm going to make 5 dice rolls. And I'm not going to pass it anything because I don't have to. And I'm going to pass this back in a tuple. And I can actually do this really easily, where I can say return, and I can just say open bracket. Remember that we can actually have pretty loose white space inside of brackets like this, and this does mean it's a tuple. Random.randint from 0 to 6. That is a dice roll, right? It is not a 20-sided die. It's not a 12-sided die. It's not a 30-sided die. Those can't exist. Fight me. 2, 3, 4, 5. And we'll get rid of this last one. Now we have a tuple, and that will return a bunch of stuff for me. So I'm just going to actually try this out. Make 5 rules, and ship it. It's a function. Spot the bug. Indeed, make 5 rolls as a function. I asked it to print a function. I need to call my function. I've been programming for more than 18 years, and I still do it. Okay, you can see my dice rolls on the side. Now we need to see if they all match. Okay, that's fine. And I'm going to make a function for that. Do all match. And I'm going to have rolls. And I can even have a doc string. Ooh, we've talked about those. To say, I'm going to return true if all 5, actually, we'll get there. Entries match. There's 2 ways I can write this. I was going to write it in a pretty stupid way, and this would be technically right. 0 is equal to, that is not technically right, is equal to roles 1. I think Python will even let me do this because Python is kind. Roles 2. Oh, this feels like a lot of typing. There's got to be a better way. Well, let's think about our data set. We know that we can actually iterate over a tuple, which is actually kind of an unusual thing to do, but in this case, it's fine. For role in roles, so a single role in there, and I'll iterate over all of them. And we can say all match is true until we prove it otherwise. And what if we have no roles? In a set of no roles, they all match, arguably. Or you could actually say they don't all match. In this case, I'm going to say if there's no roles, all those no roles match as nothing there. So now I can say what? 4, 4, 4, 4, 4. I want to put that into a comment. Is a match. And they all have to match. So I can actually compare them in 2 different ways. The way that you kind of want to do this is to compare 1 to 2, or 0 to 1, and 1 to 2, and 2 to 3, and 3 to 4. That's how you feel like you should do it. But I can actually compare 0 to 1, and 0 to 2, and 0 to 3, and 0 to 4, because they have to be all the same. So I can say if role 0 is not equal to roles. Oh boy. Roles 0, which is my first index, is not equal to the role that I'm currently looking at, then all match must be false. And now I can have a set of roles. So if Yahtzee's rules changed to pass in 100 dice, this can deal with that. This is now general. It's not hard coded to 5. So I can say all n entries, which is always exciting to me. And then I can just return all match, which will eventually be proven to be true by exhaustion, or proven to be false by just finding a role that doesn't match. So let's do a single role down here, and then we'll actually start shaping our experiment more. Def. These are all just kind of functions that make us do our job. Do a trial. Do trial. And I'm going to say make 5 rolls. I don't know. This can be a one-liner. Return. Do all match. I'm going to pass it. Make 5 rolls. This feels a little bit icky, but it also helps us see how our functions run. It's going to make 5 rolls. That will return a set of n different rolls, and I could make this into a for loop too, because why wouldn't I? And then that will get passed into do all match, and that will return a true or false for me. Cool. I'll even make a doc string. I'm going to use single quotes this time. Do a trial. Return true if they all match. And this kind of feels like it's overhead. Like, oh wow, it actually gave me a doc string. That's cool. Thanks. I didn't see you do that. Bye. Short functions are beautiful functions. I could do this in my main line, but there is enough here that I want to put it off into its own nice little function. Now I'm going to run this, and I'm going to run do a trial over here. Do trial. And false, 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 false. All right, so now I'm going to write a new function. I want to know, the question was, how many rolls does it take before I get a Yahtzee? So I'm going to say def roll to Yah. I actually had to Google it last time. Okay, I spelled it wrong. Wow. If I'm going to spell it wrong, let's spell it wrong. 1, 2, 3. And this will give me a doc string, apparently. Oh, it asked me to. Here's a little pop-up. Fancy. I hate it. Count returns the number of rolls it took to get a yeah. I have it over here. Apparently it's spelled like this. I'm copying it across. This needs 0 punctuation, am I right? And what kind of loop is this? Pause it, think about it. We don't know how many iterations it's going to take, so it must be a while loop. So our count is going to be equal to 0. And I want to make sure I don't have an off by 1 error here. While do trial. This looks not nice. Count plus equals 1. I'll actually start at 1. This is a little bit nasty code. We start at 1, we do a trial, which is our first trial. And if this returns a true, this while loop will never run. If this returns a false, it'll count again and do a trial again, and returning a true or false. This is a little bit too terse for even my likings, but we could. I'm going to prime this loop. I'm going to say done is equal to do trial. This will return true and put it into done. When I've finally got a Yahtzee. While not done, count 1, and then run this code again. This is semantically the same thing. It's nice to see it in 2 ways. This is probably how I'd actually write it because it's clear what it does. And let's spell Yahtzee right because it's actually driving me wild. Okay, so run all this. That puts it all into our memory. Roll to Yahtzee is indeed a function. Thank you. And spot the bug. This is why you test your code before you write your whole program. I've been testing each function as I write it. And that is to prove to myself that it seems to work. And 3,000. That seems very high. Wow, 177. That first roll sucked. 365, 400, whatever. So, mathematically, if we're talking about stats, your first roll will always roll a number, and then there's a 1 in 6 chance that you're going to match that, another 1 in 6 chance, another 1 in 6 chance, another 1 in 6 chance. So this is going to be 6 to the power of 4 is our hypothesis. 1 over 6 to the power of 4. That's our odds. So 6 times 6 times 6 times 6. It should be around that number. But how do we test that? Well, now we have a trial. Science requires repeated trials. So let's repeat them. So we're going to make a new function, always, to say, do many trials. And we're going to pass in how many into here. Then we're going to have a for loop. For doesn't really matter in how many. And we're going to roll to a Yahtzee n times. And this how many is really our n. And we want to keep those results somewhere. So I'm going to say my results are going to be stored in an array. It doesn't really need to be an array because I don't really need the order. But it works really nice for this because I can just use append on it. Results is equal to an array. And that array starts as empty. And I'm going to add in all my results. Results.append roll to, yes, thank you for making me not type that. And then I have to get rid of this E, which came out of nowhere. I'm going to return my results. Cool. So I'm going to run this function, and I'm going to run it with 5 trials. Always test your functions. There's often something you forgot. Okay. So now I have 5 trials, and 57 isn't too bad. Eat. Oh, yeah. There's better ways. This is a straight roll. Yahtzee, you actually get, what, 2 or 3 tries? So that's a more complicated simulation. Good. Let's get some stats. Stats is equal Stats is equal to do many trials. I'm going to pass in a constant. Constants never change. Constants never change. I want to do 1,000. I'm going to change this to 1,000,000 in a sec. You just wait. And then I'm going to have a function called print stats. And I'm going to pass in my results data. So def, what did I name it? Print stats. And this is my data. Print average number of rolls is equal to full colon. Let's do a placeholder. It's going to be a float to, I don't really need any decimal places. I'm going to do 2 and dot format, and I'm going to add a space here, and that's okay. So I'll do avg is equal to the sum of my data divided by the length of my data. And if you need to prove that to yourself, you can. And that's really the only statistic I need right now. I could actually do a standard deviation. Not really in the mood. So this should run. This is actually a whole program now, and my main line actually has a function call, and you can see it's very simple. Do many trials, and then print my stats. So that's a very simple script. That's all I really need from somebody who's reading this program. Oops. All they need to know is this, that I'm going to do many trials and print those stats. And well, each one of these functions is pretty small and really quite manageable. I'm going to change this function in a second because it bothers me. It's the only not general code here. Big stretch. Do I have to edit this program? Was 1,000 too many? Woo! That is very close to my hypothesis of 6 times 6 times 6, which was 1296. This is very close. And if I did a standard deviation, I'm certain it'd be in the first standard deviation. So now if I run this again, will I get the same result? And you can think about that while I run this. And while you can see my face of regret of doing this with 1,000. It's not. By default, random will seed itself with a random value. Now, if I set my random value, my random seed, I will do that up here. It's kind of... my seed is this. Random dot seed. I put in my seed. Now, if I run this twice, will I get the same result? I don't know actually what result I'm going to get this time. I don't even know if it's going to be close to my... wow, that is super close. Let's talk about how great science is. Over 1,000 trials, we get really dang close to our predicted outcome. And we get the exact same thing. So if you're ever doing something on your computer that involves randomness and somebody is getting something completely different on theirs, maybe try setting a seed. And the beautiful thing about this is if I had a publication that had a simulation, I could publish my code with a seed and anyone around the world could generate my exact results by hitting play. That is reproducible science. And that is a beautiful thing. And that is an actual bit of science that we wrote up here, which is pretty great. So this went on longer than I expected, but from this, you should be able to see that random numbers need not be random, but we don't have to be able to predict the next one. And then given that sense of randomness, we can actually create science. We can do random trials, and we can validate different elements of math and stats and use a simulation to show that. And sometimes our mathematical models will get too advanced that sometimes we'll only have a simulation. There's an interview, if you look at our content tool, with a civil engineer, and he runs simulations on buildings with somewhat random inputs of earthquakes. And he is doing science in no small way. And it's very compelling that we can do that with complex data sets. We can't always easily have a mathematical model. That all being said, I hope that was enjoyable. I don't often put large examples in these videos. I hope this was kind of interesting. Have a good day.